basically the same we saw in 1965. Did I run one? Oh, student.
Okay, maybe we can start. So let's start with questions from last time. Do you have any questions from last time? Okay, if you don't have any questions, I'll answer some questions that were asked to me after the lecture. So one question is, why are these divergences local? So the divergences of entanglement entropy of a region, why are they local? So that's related to the fact that in quantum field theory, recall that correlators at very short distances blow up. So it means there is a lot of entanglement at short distances. And so when we divide the region into two, the divergences are coming purely from the short-range entanglement between points or degrees of freedom in this side of the surface and degrees of freedom in the other side of the surface. So from that point of view, we expect that the divergent parts of the entropy should depend only on what's going on very close to the surface, right? And should be expressed as integrals over the whole surface. Okay. Another question is: suppose you had a scalar field in a free scalar field in a Rindler space. What can we say about the density matrix? So recall that we wrote the density matrix as e to the minus 2 pi times the boost generator. And so if we have a scalar field, can we give a more explicit description of this density matrix? What exactly is it? So you can consider the wave equation in Rindler, right? So we have some scalar field. It will obey a certain wave equation. And you could divide the field in modes, and you could, let's say, in 2 dimensions, you could organize the modes according to their frequency in Rindler time. So you do a separation of variables using the Rindler frequency as your basic variable. And in that case, you will find that the density matrix will be a product of the density matrices for each mode. So for each frequency, we have a harmonic oscillator. And for that harmonic oscillator, we have the density matrix of corresponding density matrix for a harmonic oscillator, which is sum over n of the various occupation numbers of those modes of n times e to the minus 2 pi omega n, okay, which are the energies of the corresponding oscillators. So we have this sum, and then we have the product for all the various modes. That's a slightly more explicit form of the density matrix. Okay. Now, let's erase this. Yesterday I used this Cardy formula, so I wonder how many of you would you like some explanation of where that's derived from? How many would prefer to skip the explanation? Okay. So I'll give you a sketch of the explanation together with some sketch of things in 2-dimensional field theory, conformal field theory. So everything I'll say now will apply to 2 dimensions, or 1 plus 1 dimensions. But we'll first consider 2 Euclidean dimensions. So then in 2 dimensions, the stress tensor has basically, in a generic theory, 3 components. In light coordinates, dx plus, dx minus, or in Euclidean space, we could write the metric as dc bar. So then the stress tensor will have components plus plus, plus minus, and that's equal to t plus minus. The stress tensor is symmetric, so it will be equal to t minus plus. and t minus minus. And this particular one is the trace of the stress tensor. So so this one is actually also equal. Well, we could write it as t mu mu. Okay. So in a scale invariant theory, so this we expect that we find that the trace of the stress tensor is 0. And well, more precisely, if it was only scale invariant, it is not quite 0, but it's divergence, and then you prove that it actually has to be 0. So in 2 dimensions, scale invariance implies conformal invariance, and then if the theory is conformal invariant, the trace of the stress tensor will be 0. Okay, so that's what we have. And now, if we look at the 2-point function of the stress tensor, okay, before doing that, we can say we have the conservation of the stress tensor, so d mu t mu nu equal to 0, right? And then we can write it down in this sort of like on coordinates. So we have the minus t plus plus, let's say, plus t minus plus equal to 0, right? So here we took nu to be the plus index, and then we wrote down this expression. But in a conformal field theory, this operator itself is 0. Therefore, this operator depends only on x plus, right? So this depends only on x plus and has no dependence on x minus. Okay. And similarly, for t minus minus, will depend only on x minus. Right? Sometimes this is written in terms of c, and c, so this is equivalent to saying that in Euclidean space that t c c depends only on c, so it's a holomorphic function of c. Right? This is both true classically and quantum mechanically, so we will have an operator which is a holomorphic function of c. Right? And this has many consequences which I won't be discussing. But in particular, we can ask what is the 2-point function of the operator, and yesterday I briefly discussed that. So if we write down the 2-point function of the t plus plus operator at 2 points, let's say x plus and x plus prime, right? Now we said it has to be a function of only x plus. Translation symmetry implies it's a function of x plus minus x prime plus. And then scaling, which is the fact that we can rescale all coordinates. The stress tensor is an energy density, so has units of energy divided by length. That's the same as units of energy square or dimension 2. Okay. And therefore, this whole thing should have dimension 4. So it should be a function x plus minus x prime plus to the 4th power times some number, which we're going to call c. There are some factors of 2 here. Sometimes I think this is defined with a 2. I will ignore all factors of 2 and pi in this discussion. Now, so that's the 2-point function. Now, this in particular, this 2-point function cannot be 0 because of reflection positivity. So if you are in Euclidean space, the point is that there's a property in quantum field theory that a local operator cannot annihilate the vacuum. So if you have a local operator that annihilates the vacuum, it has to be essentially 0. And now you might be surprised by this property because an operator like the annihilation operator A annihilates the vacuum. But this is not a local operator. This is the integral over space of a local operator. So then if you consider the 2-point function in Euclidean signature reflected in Euclidean time, so we know it cannot be 0. And furthermore, it has to be positive. Okay? Because this can be viewed as the inner product of 2 states. So the state that we get by doing Euclidean evolution up to here, and then the state that we get doing Euclidean evolution well, and the state here is just the reflection of this one, so it's exactly the same state, and that can be viewed as the norm of that particular state, and so this has to be positive. So C is bigger than 0, some number bigger than 0. Okay, so now let's try to check this equation that we had over there, that d minus d plus plus is 0. So now we take the d minus of, with respect to, let's say, this, let me call this x and this x. Let me set this to 0, so to have a slightly. So let's take t minus of d plus plus of this correlator, right? So we take the minus of the correlator that appears here. And you might naively say that that's 0, right? But we need to be a little more careful, because let's consider the function 1 over x plus, right? And we're going to ask whether d minus of 1 over x plus, do you think that this is 0 or not? What? Yeah, so this is supposed to be a delta function, right? Or derivative, yeah. So this is a delta function, delta square of x, right? So it's delta of x plus times delta of x minus. Okay. Now, why is that? So we can think of 1 over x plus as d plus of, let's say, the log, for example, of modulus of x plus x minus. And if we think about it this way, then this is like saying like the Laplacian times the logarithm of x, which, and the logarithm, recall, is the inverse of the Laplacian in 2 dimensions. That's a delta function. Right? Alternatively, we can think in terms of a contour integral. I mean, this type of so this is the gradient of another gradient. So we could take a contour integral, and due to the presence of the pole, that will have to contain this delta function. So anyway, so that there is this delta function, and so what that is saying is that it is fine to think of x as holomorphic as long as x is not quite on top of the other point. And the equation, so if we take this derivative, then that equation, so the equation d minus of t plus plus equal to 0 is not obeyed. So it's obeyed as long as x is different from the insertion of this operator, but if we ask about the point where x plus is equal to 0, then it will not be obeyed. Therefore, we will have to add, so that is, we could fix that if we say that d minus minus, so okay, let me say what this is, so that so we said that the derivative of 1 over x plus is the delta function. So this is a delta square of x. Here we have 3 more derivatives of x plus. So this is d plus cubed of delta squared. Okay. And now let's postulate that this correlator x plus x minus is equal to delta squared of x plus x minus d plus square d minus. Okay. So let me see if I got everything correct. So what we want is that when we take d plus of this quantity, right, which is what appears there, we should get exactly the same as we were getting here. So yeah, so I forget about this d minus. So what? Yeah, sure. So what I'm saying is we're trying to fix up this word identity here that comes from something very fundamental like the conservation of the stress tensor, right? And in order to fix it, we are going to add a contact term in the 2-point function. So contact term means a term which is only non-vanishing when the 2 operators are overlapping, right? So it will be some delta function, and because of the plus indices, it has to have this extra derivative, and now the dimensions work and so on, so it has to be something of this form. And we're going to adjust the coefficient. So here we had the coefficient c. We're going to adjust the coefficient in such a way that that equation is obeyed. So the left, so the top part is this term here. We have d minus d plus, and so if we take d plus of this, which is what we get here in this term of the equation, we see that we can make the equation of A if we put a factor of c. Forget about the minus signs. I'm not... OK, this derivation, as I said, there will be a minus sign here. But you can check all the signs yourselves if you want. If you really want to understand it, then normally if you want to really understand something, you need to understand all two minus signs and so on, and then you really understand. So this is just a sketch. OK, so what is this sign? Yes. Yeah, so if we have this derivative, then we get a delta cube. That's correct, and then they cancel, right? And indeed, then we remove one of the derivatives. Then we have this expression, and now we'll see what this expression implies. It erased. Yes, sir. Well, good. Yeah, so it's, all twos are important in this. to really understand it, yeah. OK, so now what we will do is we will so consider this to be x prime, right? So this is now x minus x prime. And then we multiply by, let's say, some small function g plus plus of x. So the stress tensor is what results from doing a small change in the metric. And then we integrate d squared of x prime, right? So if we do this integral, then what we get is we here multiply by the same function and so on. And what we end up getting is something of the form c times d plus squared of delta g plus plus. Okay. And then we could also have a similar thing with minus minus, and we'll get also another expression where we will add to this the minus minus. And this expression can be viewed as the linearized curvature. So this is some expression. And if you take the metric of flat space and you make a small deviation of the metric, you can ask what kind of invariant tensor this is. And it turns out that it is the small variation of the curvature. In other words, if we put the field theory in a curved background, what we'll find is that the expectation value of t mu mu, or t plus plus, is going to be equal to the central charge times the curvature. Again, I'm not keeping track of the numerical factors. So here all we derived was the expression, just the linearized expression around flat space. And from this, and saying that, well, whatever this trace is, it should be a local expression in terms of a local expression in terms of the background space. So here what we're imagining is that we put in the field theory on some curved background and with some generic metric, g mu nu, two-dimensional metric g mu nu, and then we get that the trace, which naively would be 0, and it is almost 0 because it's just a C number, so it's not an operator in the theory, right? It depends on the metric of the space, but the metric is a parameter of the field theory. It's not an operator in the field theory. So the trace is just this curvature. Okay. And right. So this is sometimes called the conformal anomaly equation. So because one might have naively expected t mu, the trace of t to be 0, but it's not quite 0. There is some small dependence in the theory. There is some small scale dependence of the theory. So naively one would have thought that if you take a metric and you change the metric, let's say 1 plus delta some function, we rescale the metric just slightly by a small quantity, then one would have expected that to get exactly the same partition function, for example. But this equation is saying that we are not going to get the same partition function but that there will be a change in the partition function that will be proportional. Yeah, I should write bigger. Delta of log of c, which will involve this the integral of the delta omega, so the change in the scale factor, times the curvature of the original metric, right? Okay, times some factor of c. And you can view this as saying that, well, when we define the theory, we'll need to regularize and we'll need to subtract some divergences, and there is some residual dependence of the scale factor of the metric in this subtraction. So typically you will have logarithmic divergences, you subtract something that diverges, but you will get some still finite dependence on the scale factor of the metric. But the dependence is simple. It's just in a C number that depends only on the metric, not on the fields of the theory. Here I haven't mentioned any operator of the field theory, only the external metric. Okay. So this is what happens under a small change, and if we can sort of integrate this equation and consider a finite change. So what happens when we go from g mu nu to e to the 2 omega g mu nu, right? Or maybe let me call this g mu nu hat so it's clear what we're doing. So then the idea is that the ratio of the two partition functions, or the difference in the log of the two partition functions, is going to, well, we can get it by integrating this equation. And we get that is equal to c times the integral of the gradient of omega. So all these gradients are with respect to this metric here, plus some term of the form omega. Okay, and this is sometimes called the Liouville action, though sometimes it should be called the Polyakov action. But the Polyakov action should be called something like the Nambu action. But anyway, so we are not going to reinvent the name. So this is something that was derived by Polyakov. Anyway, so now there is something interesting here, which is going to relate the stress tensors computed with respect to the metric G. So let's say that we define the stress tensor with respect to the original metric G. And that's going to be equal to the stress tensor. So now we can take the derivative, the functional derivative with respect to the metric. And there will be a contribution from taking the derivative with respect to the metric G hat here. So on one hand, we have just the usual stress tensor defined in terms of the metric G. And on the other hand, we have the stress tensor of, let's say, the Liouville part, which will involve d mu omega. So let's say around flat space is just going to be an so let me just consider only one component of the stress tensor. So it's going to be something of the form d plus omega square plus d plus square of omega, and this second term comes from this term here. And then we have the d plus plus in terms of the metric G hat. Okay. So this is just the stress tensor measured, or with the theory renormalized with the metric G. And we can compute it in any coordinate system and so on, transforms appropriately under coordinate transformations. And it's equal to this expression in terms of the other metric. So now it's interesting to consider a situation where we have two metrics. One, so let's see. I guess perhaps we'll do it in Euclidean space. So let's consider, on one hand, flat space metric, dc squared. And on the other hand, let's write c equal to e to the omega, right? So it's an exponential map. So this original metric is equal to the metric e to the omega plus omega bar, d omega d omega bar, right? So this metric is the analog now of the metric G, right? The one in the left-hand side. And this will be what we were calling e to the 2 omega. Okay. So this is a map that maps the plane to the cylinder. So let me be a little more precise. This is very closely, this is almost closely related to what we were doing with Rindler space before. So we have the plane C, right? And then something, so the variable W, so if we just change the imaginary part of W, we are going to move along circles here in the C plane, okay? So this metric here has some translation symmetries in W that correspond to scales and rotations of the original metric. Okay, very good. So then, so the original, we have, let's say we had the vacuum in the original space. So in the C coordinates, we have the Minkowski vacuum, and we normalize the stress tensor so that t is equal to 0. The expectation value of t is equal to 0 in that vacuum. So t cc is equal to 0, right? But now we come back to this expression, and we, well, I guess now we're using variable c. And now we just evaluate this. So notice that omega is just linear in this variable, so something with a second derivative will drop out. And here I should really put omega. So something with the second derivative will drop out. And so we only get this term. And that's just a constant, right? So this is omega is just omega is simply omega plus omega bar over 2. So these derivatives are just a constant, and I'm not keeping track of factors of 2. So we get some expression of the form c some constant and then t w. Okay. And this is the stress tensor measured with respect to the metric g hat, which is just the metric dw bar. Okay. So here we have a metric which is the metric of a cylinder. So this is the, let's say, real part of W, and this direction is the imaginary part of W, right? It's a cylinder because the imaginary part of W was this rotation coordinate here in the C variable, right? And was periodic, right? It goes from 0 to 2 pi. So here we have the metric of a Euclidean cylinder. And we are getting that the stress tensor on this cylinder measured with respect to the flat metric on the cylinder, so with the theory renormalized with the flat metric on the cylinder, is some constant, right? And so that's so this right-hand side can be viewed as the CFT at finite temperature, right? Some temperature which is 2 pi in this case, okay? And this is telling us how much the stress tensor, how much the energy is, the expectation value of the energy is in the energy density is at that particular temperature, right? So this is telling us that the expectation value of the energy at temperature 2 pi is goes like C. And if we now we want the energy density at some other temperature, how do we restore the factors of temperature? Imagine we computed everything with the proper numerical coefficient so far. How do we restore the factors of temperatures for generic temperatures? So now consider a cylinder that has a generic temperature beta, right? What should we put here? Huh? Yeah, the dimensions, dimension analysis, right? How many powers of the temperature do we expect here? Right. So we'll get a factor like this, right? So a factor like this will give us the general dependence, right? Just by scaling. Once we computed the proper factor here, and the proper factor can be computed by doing this whole thing with all the numerical factors. And I think yesterday I quoted the right factor. Well, I quoted the right factor for the entropy density. So once you have the energy density, you can compute the entropy density. And yesterday I quoted a factor for entropy per unit length, or entropy density, which was 2 pi t times C over 6. Okay. Okay. That's so far. That's the Cardy discussion. Now another thing that is usually said in this context is so this computation can also be viewed as a computation. So what we said so far, we were viewing this direction as Euclidean time. But we could also view this direction as Euclidean time, and this direction as a compact spatial circle. And then exactly the same discussion now has the interpretation of the calculation of the Casimir energy on a circle. So we have the quantum field theory, which in flat space had, let's say, 0 energy density. We put it on a circle. Due to the fact that we put it on the circle, there will be a non-zero energy on the circle. And that energy on the circle, again, will be proportional to C. So it will be some factor of C. And when you think about it properly, so for a circle of radius 2 pi, this factor is C over 12, okay, with a minus sign. So that's, again, a generic answer for any CFT. Once we do this. So in 2 dimensions, there are many quantities that are governed by this number, the central charge. The reason it's called central charge I didn't explain. It's related to the fact that there is the Virasoro algebra, and this number appears in the Virasoro algebra in a way that it commutes with, so it's just a constant, it commutes with all the other generators, and that's why it's called central. And it's called charge because it's some extra number. You could think of it as having some different eigenvalues on different theories, but normally we just think of it as a C number. Okay, so that's. Are there any questions about this? 1 over r. Yeah, that I said it was for a circle of radius 2 pi, of size 2 pi. But indeed, if it has a generic size r, then we have r, where r is, yeah. So in the same way that we got the behavior for any, so that was for size 2 pi, right? And then if we have any other beta, we have 2 pi divided by beta, right? Beta is the size of the circle, right? That's the total energy, yeah. Very good. So now, so we said all this, and recall that last time we had derived the formula. So based on essentially this formula, we derived the formula for the entanglement entropy of an interval. So if we have a 2D CFT and we have an interval, then yeah, so to be honest, the things that I've said so far are for theories where C left is equal to C right. So to get there, the curvature, we assume that C left was equal to C right, if you know what that means. That means the coefficient that appears in T++ is equal to the one that appears in T minus minus. And I'll only discuss such cases. So we derived the formula for the entropy of the interval, which was C over 3 times the log of the UV cutoff divided by the size of the interval. Right? Okay, so that was this case. So now let's. So what I'm going to start discussing now is an application of these entanglement entropies ideas to derive a so-called C-theorem. So a C-theorem is a theorem that says that a certain quantity decreases under the renormalization group flow, so that if it's larger in the ultraviolet than in the infrared. And in this context, it was originally such a C-theorem was described originally by Samolochikov, where he defined the function C. So, first of all, the C-theorem is useful when you are doing non-conformal theories. So in a conformal theory, that quantity C that you define is constant. It's like the central charge. Doesn't depend on scale. It's just a number. But when you are considering theories which are not conformal, that flow between a ultraviolet fixed point, conformal field theory in the ultraviolet, and an infrared, let's say, conformal field theory, then it should decrease, right? It should be less in the infrared than in ultraviolet. And then you'll have to define this quantity C. And well, Samolojikov gave some definition in terms of the 2-point functions of these various components of the stress tensors. So there are 3 components of the stress tensors in the non-conformal theory, and you can define it in that way. And then use both reflection positivity and this condition to derive an inequality. So now we are going to do the same, but using entanglement entropy. But we're going to define the function we're going to define is going to be slightly different than the one Samolojikov defined. What I'm going to discuss now was done by Casimir and Huerta, and it's a little nicer in the sense that it's a more direct connection to the number of degrees of freedom. The intuition is that as you go from the ultraviolet to the infrared, the number of degrees of freedom should decrease, the number of fields should somehow decrease, and the question is whether this is true or not, right? So that's in relativistic quantum field theories. We expect that the measure of the number of fields, which in the 2 dimensions a good measure seems to be this C. It appears everywhere, so we'll take it to be a measure of the number of degrees of freedom. Maybe I should have said that, for example, for one real scalar field, C is 1. For one Majorana fermion, C is equal to 1/2. And then you can have all kinds of theories with various values of C. But anyway, so now we're going to do a non-conformal theory. Let's imagine that this non-conformal theory has a ultraviolet fixed point. So let's imagine that in that theory, so it's again a 1 + 1 dimensional theory, and we are going to compute the entanglement entropy of an interval of length L. Okay. Now, what do you expect the diversion part of this entropy to be? So this, there will be a cutoff. There will be some terms that will be divergent coming from the endpoints of the interval. Do we expect the power of epsilon or a log of epsilon? Log. What do you think the coefficient will be? So this is a CFT that in the ultraviolet, at very short, this is a non-conformal theory. Then in the ultraviolet has an ultraviolet fixed point. So an example of such a theory would be a real scalar field with a mass, for example. So at very short distances, it is as if it was massless. Long distances, we have some mass. Yeah, so here we'll have CUV over 3, right? And then here there could be some generic function of L, right? We don't know what. So before we knew what the function was, it was just this log of L. But now that it's not conformal, we don't know what it is. Okay. Now we're going to define some C of L. So this is going to be our C function. We're going to prove it has the property of a C function later, but it's going to be a function, and we're going to define it in terms of this entanglement entropy as in such a way that we get rid of these diversions. And a good definition is to say that this is 3L dl of S of L, right? So if we define it this way, so this is just a definition, but the only thing at this point I want to point out is that if we define it this way, the divergence drops out. Okay, so we're comparing the entanglement entropy for, let's say, an interval of some length with entanglement entropy with an interval of a slightly different length. So this is an example where when we look at a useful function that will be useful for something, the ultraviolet divergences will drop out, and you will typically want to describe to consider such functions. And of course, this is just 3L dl of f, this function f. Okay, so now one can derive. I'll show you the derivation in a second, but let me just first state the result. That dl of C of L is less or equal than 0. Okay, and this will follow from Lorentz invariance. And some entropy inequalities. So if you want to say it's unitarity in the end, I mean, it's the fact that all these entropies come from density matrices, which are positive matrices. Okay, so I'll tell you the derivation in a second. But first, one thing I forgot to mention is that if you have a conformal field theory where f of L is this log of L, right? So using this definition, you will get that this C is this constant that we have over here, right? Did I mess up the sign? I probably messed up the sign. Okay, yeah. Deriving that is that it decreases when it has the wrong sign. That would be bad. Okay, so. Yes. The one I wrote over there? Yeah, that's the total entropy of this interval, the von Neumann entropy of this interval, which in this case that we are starting with the vacuum is just the entanglement entropy of this interval, right? So
this is dimensionless, right?
Yes, it's dimensionless. So here, this can be an arbitrary function of L because there could be other scales in the problem, like the mass. So in this example that we discussed with the massive field, there would be some mass here, and then, well, L times m mass, and then, yeah.
You probably had the right sign before you could find it. Because your case of log, and now you have.
Well, it's minus log L, right?
Yeah, minus plus.
Well, how many? Well, you can check what the correct sign is. Ah, that's why I had the wrong sign. Yeah. Okay, good. Yeah, I was worried about this sign because the inequality was working correctly with this sign. I was going to have to find another mistake in the rest of the derivations, which I was getting worried about that. So these are mistakes just to make sure that you're paying attention. Okay, so the argument is very nice, and it considers. So let's consider. So we have the Lycon, right? And so let's say this is x minus, and this is x plus. And so let's consider. So this is 1 and 1 here, right? So let's consider this interval, right? That's one interval we could consider. Its length is equal to the square root of x plus x minus, right? So we are going to consider here various intervals, and their lengths are going to be the product of x plus x minus. So so if we have an interval that ends at some generic position of this kind, so the length, for example, of this interval will be equal to the square root of x plus x minus. Okay. And good. Now, when we consider the entanglement entropy of an interval like this, we could also consider a boosted interval, such as this interval, right? And the entanglement entropy associated to this interval will be a function purely of the length, of the proper length of this interval, which in this case is just the square root of x plus, right? Well, x minus is 1, right? Okay, very good. So now we'll consider in this argument this various intervals. So one will be this interval here, and we're going to calculate the entanglement entropies for the various intervals and consider a particular entanglement inequality. Yeah, let's see. Let's write it here. Well, let me erase this formula. So the inequality we are going to consider is called strong subadditivity. Okay. And it says that if you consider the entanglement entropy of so strong subadditivity is an inequality that involves three regions. So regions A, B, and C. Okay. And so we're considering the entropy of A union B union C plus the entropy of C is less or equal than the entropy of A union C plus entropy of B union C. Okay. And so this is not so easy to prove for density matrices, and it was proven by Liouville and Ruskay. And it can be proven with not much difficulty from the monotonicity of relative entropy also. So those two are the hard ones to prove. But if you prove one, you can prove the other. Yeah, so that's the basic one we are saying. But you can think it's plausible by thinking about A, B, and C, right? And then imagine that you have pairs which are entangled across A and C, and you can have things which are entangled between A and C, or between C and the rest, right? So you can consider a situation of this kind, and you can, by counting lines, you can easily see that this is going to be obeyed. Okay. If you don't have these kinds of lines, this will be saturated in this picture. You can consider lines where you entangle all three of them, and then it will not be saturated. But anyway, so you can make this plausible in this way, but to find a correct mathematical proof is a little more difficult. But it can be done, and it's not infinitely long, but it's not very intuitive. At least I didn't find it intuitive enough to remember it. Okay, so now we are going to be considering these various intervals, and we'll think of this interval as C. Okay, so this interval here would be C. We can think of this guy as A, and so the entanglement of, more precisely, then we're going to consider this whole interval as A union C. Okay. And then similarly, this could be viewed as B. B we don't really need, so don't worry too much that this is Lie-like, right? What we are really using is what B union C is. So this is B union C. This is some other interval. And then if we consider the whole thing, then this is A union B union C. That's the top interval. Okay. So S is a function of L, right? And just to make the argument somewhat simple, so imagine that this is at the point e to the delta, and this is at point also e to the delta, right? So this is at 1, and this is e to the delta. Delta will be small. And so these entropies are a function of L. And so we'll get here S of e to the delta, because it's the product of this times that square root, so that's e to the delta. This is the entanglement entropy of an interval of length 1. Okay. And this is less or equal than the entropy of an interval of length e to the L, delta over 2, plus S of e to the delta over 2. Right? Okay. So that's what we derived so far. So this is the this came from essentially unitarity of the theory and the positivity of the density matrices. Here, in this formula, when we wrote these particular dependencies on the position of the endpoints of the intervals, we use Lorentz symmetry, right, to calculate how the entropy depends on the size of the interval. And now we are almost done, so we can, if you wish, we can call this function, let's say, h of delta, right? Let's call this function of delta h of delta. And so we now expand this function up to second order in delta. So this is going to be h. This would be h of 0. And this would be h2 times h of delta over 2, right? And now we expand to first. If we expand to first order, we'll get h prime here and h prime here, and they will cancel to first order. So, and then we now expand to second order, and we get here h double prime delta square is less or equal than twice h double prime delta over 2 all squared, and this is equal to h double prime delta square over 2, and then we end up with the condition that h double prime is less than 0, right? But what is derivative with respect to delta? So the derivative with respect to delta is the same as L dl, okay? And therefore, this function h prime is exactly the same as the function, well, it's proportional up to a positive constant to the function C of L that we define over there, right? Recall the definition of C of L with the sign that you guys corrected. You helped me figure out the correct sign there. And that function is exactly the same as the first derivative of this h. And now the second derivative is negative, which is the equality we wanted to prove, right? The inequality we wanted to prove. Okay? So that's the end of the derivation. Where Lorentz symmetry came in? Yeah. Lorentz symmetry came when we said that so first of all, we said that the entanglement entropy is a function purely of the proper length of the interval. So if we have an interval of this kind, it's going to be, well, just the length. But before we were considering purely spatial intervals. So the novelty here is to start considering these tilted intervals, right? So, and so when we consider this other interval, the entanglement entropy associated to this interval is going to be proportional to the proper length of that interval. We would go to another Lorentz frame where this is just a spatial interval, right? And in that Lorentz frame, the entanglement entropy is just is given by the same function that we had before of the length of the proper length of that interval. So that's where we use Lorentz symmetry. Okay. Now, this was extended to 2 plus 1 dimensions. And so here one re-derived the result that one knew before. It's not exactly identical because this function C is not the same function that Samolochikov defined. But well, it shows the utility of thinking about these entanglement entropy ideas to derive, let's say, theoretical results in quantum field theory. And the same can be done in 2 plus 1 dimensions. So in this case, you consider the entanglement entropy in the vacuum. So the vacuum entanglement entropy. So we have the vacuum and we have a disk. So we have 2 spatial dimensions. So we consider a disk in those 2 spatial dimensions. And so here, what did you expect the diversion terms to be? So here we said they were going to go like r over epsilon. And then there is going to be something finite. So in a non-conformal theory, this finite piece will depend on R. And in a conformal field theory, this just would be just a constant. Okay. So here it's convenient to define a function f of R. So even in non-conformal theories, we can define an f of R which is equal to R dr minus 1 times this S of R. Right? So if you have a term that is linear in R, such as this term, it will drop out from this expression because R dr will give us this term back, and the minus 1 will just remove it. Right? So this gets rid of this particular derivative operation, gets rid of the diversion terms in a way very similar to the one we used before. And it lets us focus on the finite piece. If we have a conformal field theory, so we just get rid of this term and we just get purely the finite piece. We get minus the finite piece. Okay, this f of R would be minus the finite piece. And it turns out that so there the argument is more complicated, and I won't discuss it. But you can argue that this f of R also decreases. So f of R decreases. Under the renormalization group flow. So it's a more sophisticated argument, not with just a couple of intervals, with an infinite number of different spheres that are all boosted relative to each other and so on. But it's the same, conceptually, it's the same idea of using entropy inequalities and Lorentz symmetry. Now, it turns out that this quantity is, in three-dimensional field theory, is related to some other quantities in the same way that the C function appears in various observables. This quantity f for a conformal field theory is related to the S3 partition function. So if you take the partition function of the field theory on S3, right, then this partition function is equal to e to the f. Okay, so for a conformal field theory, f just is a constant independent of R, and the partition function is just equal to that constant. Now, at this point, you might worry that this partition function has divergences. So when you consider the partition function on Euclidean S3 has divergences, but those divergences are local and have the form 1 over, let's say, epsilon cubed. Well, maybe I should write bigger. Okay, good practice to write bigger and higher. Okay, so the partition function of a field theory on conformal field theory on S3 will have diversion terms that go like e to the integral over the volume square root of g times 1 over epsilon cubed. And you could also have diversion terms that go like the integral of square root of g times the curvature of the sphere. And then we'll have this finite piece that is the one we were talking about. So the statement is that we can unambiguously separate these volume divergences and concentrate on this finite piece. Now, very good. So why are these two things related, you might ask? Sorry, I screwed up the sign here again. Well, we would have discovered it in the derivation. So why are the two things related? So we can think of S3, right? So we start with S3, and we can choose another conformal frame. So do a rescaling of the metric, so that we go from S3 to H2 times S1. Okay. Now let's I could do this more explicitly. So suppose you had the metric in these coordinates. What do we call this one? The phi. Okay. So that's just the metric of the sphere. And now to go to the metric of h2 times s1, we just divide everywhere by cosine square of theta. These two metrics differ purely by conformal factor. Okay. And so the partition functions for the theory on S3 and the theory on H2 times S1 are going to be related. Okay. Now we have to worry about conformal anomalies as we had to worry in 2 dimensions. However, in 3 dimensions, you do not have a conformal anomaly because when you take the trace of the stress tensor, whatever appears here has to be a local expression. So a local expression in terms of the metric, for example, and the curvatures and so on. And the metrics, the curvature has dimension 2, and the Riemann tensor has dimension 2. And so any contractions of the Riemann tensors and so on we can make will have even dimensions. So in odd dimensions, we don't get, there is nothing we can write down, and the theory is also Weyl invariant, and there is no conformal anomaly. So things are simpler in odd dimensions. Okay, so that's so far. So these 2 things. Now H2 times S1 can be interpreted as a thermal theory. So the thermal theory on H2. So you can think of S1 as Euclidean time, and so then this is a theory at finite temperature, at temperature 2 pi, at beta equal to 2 pi, on H2. Okay. And if we do that, then we find that what we are calculating, this partition function, can be viewed as e to the s minus beta times the energy, right? So that's just the free energy expression. So that's S is the entropy of the theory on H2, and E is the energy. So the energy can be computed in terms of the expectation value of the stress tensor on this space. Recall in 2 dimensions we computed the expectation value of the stress tensor after a Weyl transformation by using the conformal anomaly and so on. But here it's even simpler, because there is no conformal anomaly. The expectation value of the stress tensor on H2 times S1 is going to be 0, because it was 0 on S3. So the 1-point functions are 0 on S3. And so E is actually 0 at this particular temperature. Of course, if you were to vary the radius, then E will have different value, and this will not be true. But at this particular temperature, the partition function is just the entropy. Now, this entropy is also essentially this entropy, because if we have a circle, let's say a circle in space is also related to H2 times S1. So it's also related to a thermal theory in H2. Maybe how well will I explain that? Should I explain it in detail? Yeah, I'll explain it in detail. So a disk. So far what we've shown so far is that the partition function on S3 is the same as the entropy on H2, right? Times S1 with period 2 pi. So that's what we've shown so far. Now, a question? No. Is there a question? Yeah. It wasn't the metric on S3? Well, I probably made a mistake. Let's see. No, I think it was the metric on S3, right? Well, the original metric on S3, well, S3 has 3 dimensions, right? So we have 3 coordinates, right? So yeah, these are not exactly the Euler angles, but you might be more familiar with. But they're simply related to the Euler angles. But in order to understand the origin of this metric, is convenient. So you write the sphere, the 3-sphere. Right? So then psi is the angle between here and here, right? So you write x1 as, so okay, but let's be very explicit. So x1 will be sine of theta times cosine of psi. X2 will be sine of theta sine of psi, right? And so on. And these two, so the sum of these two squares, so this whole thing is going to be called sine square of theta. And this whole thing is going to be called cosine square of theta, right? And then the rest is clear. Very good. So now you know that by just the conformal transformation, we can map the disk to a plane, right? So the disk can be mapped to a plane. And if you had the plane, so to the half space, so the disk, since conformal transformations mapped circles to planes and so on, so we have that we will have a particular conformal transformation that maps this, so the interior of the disk, to a half space. Right? So this is the space, for example, so we have some coordinate, let's call it, anyway, so we have some coordinate, let me see, how are we choosing the coordinates? Yeah. So we have, let's say, one spatial coordinate x, and then we have the Euclidean time coordinate, and then we have a third coordinate, right, that goes in this direction. So we can, let's see what is most convenient here. Right, and then we can use now the usual discussion that we were discussing before in Rindler, right? So there is, so in this half space and Euclidean time, we choose Rindler coordinates, the r squared plus r squared, the theta squared, right? This is not the same theta, well, how should I call it? The alpha squared, okay? So alpha is this coordinate. And then there is a third coordinate, which I'm going to call dx parallel. Right? So that's Rindler space plus the extra coordinate, and those were useful coordinates for thinking about the half space. And now we can divide by r squared, and so we just have these two divided by r squared plus the alpha squared, and then this looks like the metric of H2, right? And then this is ds1 we were talking about. So what we did was to relate the disk to the half space and then do a Weyl rescaling of the metric so that now we have H2 times S1. Okay. And the original entropy we wanted to compute, well, what was it? It was the entanglement entropy of the density matrix coming from the evolution in the angle alpha. Remember yesterday? We talked about that. And that translates into just the ordinary thermal entropy in this situation. So it's the entropy we get by doing Euclidean evolution in this S1. Okay? We have no conformal anomaly to worry about, so then this entropy is actually equal to the entropy we talked about here, right? And in a conformal field theory, this finite piece defined with things defined this way is minus f. And the divergent pieces are not tracked through this argument, but the finite pieces are, and we get in the end that this was 0 and s was e to the minus f, and that's the relationship we wanted to prove. Okay. Now this f has so the story here in 3+1 is slightly different than the one in 1+1. So in 1+1, this function c appeared in the 2-point function of the stress tensor. We don't know how to relate f to correlators of the stress tensor. So if you take the 2-point function of the stress tensor, you will have another number there that is not equal to f. So here we only related these two quantities. And one nice feature is that this partition function on S3 in many supersymmetric theories is exactly computable. So in three-dimensional theories with at least n equal to 2 supersymmetry, there is a technique based on, it's called supersymmetric localization, that actually allows you to compute these partition functions. And so you can check this and you can see it's true. And in fact, the fact that this was some kind of f function was conjectured before based on the explicit computations for of this kind. Okay. Now, one thing you can wonder about is, let me say one more thing related to this. So when you have this disk, well, this relationship between entropy and partition functions is very general. I mean, it's true in other dimensions also, but in even dimensions you have to worry about the conformal anomaly. In odd dimensions it's essentially the same as what I said so far. But it's not as calculable in other dimensions. Well, except in 4 dimensions where it's related to the A anomaly, which also is simple. Now we have this disk, and you might wonder what the... So we had the Killing vector, which... yeah, so what I'm going to try to explain now is the following. In Rindler space, we found that the density matrix was equal to the integral of a local e to the integral of a local operator, right? E to the boost. Remember that formula? Rho equal to e to the minus 2 pi b, right? And due to this relationship, the same should be true of the disk. And so I like now to give us more explicit discussion of what exactly is the operator that appears in the disk case, right? So you can... So what is B? B is sum of the generators of the conformal group, right? So it's B is the integral of the stress tensor T mu nu times particular conformal Killing vector. In this case, it's just an ordinary Killing vector. The star of this is the current that they integrate on a spatial surface, right? So this is a conformal current, right? Current associated to the symmetry generated by zeta mu. Which in that case was just the boost. And here, yeah, maybe I should go through this a little more slowly. So if you have a symmetry, conformal isometry generated by the Killing vector zeta mu, right? So for example, if you had a translation, zeta mu is just a constant, right? So you have a small change of variables, which is so x mu goes to x mu plus delta mu, delta x mu, and this is, let's say, what we are defining as xi mu. Let me just write it like this, which in general could be a function of x, right? So for the case of translations, zeta mu is just a constant. So associated to any such symmetry, there is a conserved current, J mu zeta, so it depends on the Killing vector that you chose, conformal Killing vector that you chose, and it's equal to J T mu nu zeta nu. Okay. So you can check that this is conserved because you can hit it with d mu, right? So we'll and well, here d mu of t mu nu that will give us 0, right, by current conservation, by the stress tensor conservation. Now, of course, there is a term where d mu acts here and a term where d mu acts on the... Yeah, maybe I should go through this more slowly. D mu j mu is equal to 0. So it will be a piece where we'll get d mu of t mu nu, right? So So there is this term, and then there is a term where we get d mu nu, d mu, zeta nu, right? Well, the indices are contracted in the appropriate way. Let me just write this. Okay. So in this piece, this guy is 0 because of the stress tensor conservation, right? And this one here, so if we have a conformal Killing vector, then we know that d mu nu symmetrized is proportional to g mu nu or eta mu nu. So in the flat space case, it's proportional to eta mu nu with some function, some proportionality constant, which could be a function. And well, of course, this function is nothing else than the sigma zeta sigma, right? Okay, so this piece is proportional to the metric, and the trace of the stress tensor is 0 in a conformal field theory, so then we'll get that it's conserved current. And that's what we used there, and this we can do for any generator of the conformal group. And what was the boost generator in these coordinates after we did the conformal transformation to the half space? In the original picture is some conformal Killing vector that preserves the boundary of this disk. So it's some Killing vector that in Lorentzian signature has an action of this form. So it preserves, it maps points inside the causal wedge to points inside the causal wedge. And we can give it a very explicit expression. So C mu, so let me, C mu dx mu is equal to 1 over 2r. R squared minus the spatial coordinates minus the time coordinate. This is the Minkowski time coordinate in this picture times dt minus 2 dx dx. Okay. Anyway, it's not too important to know exactly what it is. What's important is that you can write it down, and how we obtain it is by. So if we think, well, we can just ask for what is the conformal isometry that preserves the boundary of this disk, and we'll get just this one. And then we can now write we can write now formula for the density matrix of so before we wrote e to the minus 2 pi b, right? And for this case of the disk, we can write similarly, rho is equal to e to the minus 2 pi times the integral over space over the disk. Let me call it the spatial disk of the star of t mu nu zeta nu, where t is the stress tensor of the field theory. Zeta nu is that Killing vector that we wrote over there. And of course, this is just the dual, so the epsilon tensor. So the important thing is that this is also a local operator in the field theory. So both the half space, so this was Rindler. So Rindler has a simple expression for the density matrix for any field theory, conformal or not conformal, any Lorentz invariant field theory. If it's not Lorentz invariant, then the thing doesn't work. But if it is Lorentz invariant, then it will have the simple form. And in the case of the disk, it also has